Hello, I'm Laura Marshall.
And I'm Melilnda Rose, and this is Light Matters for June 19th, 2013.
On today's show, light scattering and nanolithography combine for drug delivery, quantum dots bring together the best of optical and electron microscopy, laser-driven neutrons could neutralize nuclear smugglers, and a new metamaterial design aims to replace bulky optics.
Researchers at North Carolina State University applied their knowledge of light scattering by particles to nanolithography to create a potential drug delivery system they dubbed a nanovolcano. They used nanolithography techniques to create the device, placing transparent nanoparticle spheres directly on a thin film that changes chemically under UV light, turning the film into a small mound with a hollow core. These nanovolcanoes can store and release precise amounts of materials, and their shape and geometry can be precisely controlled, making them suitable for drug delivery. The materials used are relatively inexpensive, and the process can easily be scaled up. The investigators are now working to improve their understanding of the nanovolcano's release rate, including how quickly nanoparticles of different sizes will escape from different sized cavities. The research appeared in ACS Nano.
A fast, versatile, and high-resolution technique that combines the best of optical and scanning electron microscopy evades two problems in nanoscale microscopy: the diffraction limit and relatively high fragile specimen-destroying energies. The microscopy method developed at NIST uses a process similar to how an old tube television produces a picture, a process called cathodoluminescence, and could provide surface and subsurface viewing of features as small as 10 nanometers. Much like in an old tube television where a beam of electrons moves over a phosphor screen to create images, the new technique works by scanning a beam of electrons over a sample coated with specially engineered quantum dots. The QDs emit low-energy visible light very close to the surface of the sample, exploiting near-field effects of light. After interacting, the scattered photons are collected using a photodetector. The first demonstration imaged the natural nanostructure of the photodetector itself. Because both the light source and detector are so close to the sample, the diffraction limit doesn't apply. The work was driven by a desire to study how inhomogeneities in the structure of polycrystalline photovoltaics could affect the conversion of sunlight to electricity and how such devices can be improved. But the team quickly realized that the technique could also be adapted to other research regimes, most notably imaging for biological and cellular samples, as well as organic photovoltaics. The research appeared online in AIP Advances.
A single short-pulse laser-driven neutron source could make it much easier to detect nuclear materials smuggled in shipping containers. Active interrogation involves directing nuclear radiation into a closed container and measuring secondary radiations to gain information about the contents of the container. Detecting nuclear material using this method is currently impractical because it requires a giant stationary facility or long measurement times with less powerful neutron generators. The short-pulse laser at Los Alamos National Lab's Trident facility was used to demonstrate a laser-generated neutron beam with novel characteristics that interrogated a closed container to confirm the presence and quantity of nuclear material. The successful experiment, which involved directing a powerful laser burst into an extremely thin foil target to produce neutrons, paves the way for creating tabletop-sized or truck-mounted neutron generators. Neutrons are a good choice as a probe because they can penetrate most materials very easily and release even more neutrons if they come into contact with nuclear material. These delayed neutrons are a good measure of the presence of nuclear material because very few other materials produce them. The Los Alamos researchers interrogated two containers, one empty one and a closed one containing nuclear material. They discovered that the laser-driven method confirmed not only the presence of nuclear material, but also the quantity, something that had never been demonstrated before.
In more news from Los Alamos, a metamaterial designed there aims to replace bulky optical devices to improve IR cameras, energy harvesting, security screening, and radar systems. The researchers demonstrated ultra-thin, broadband, and highly efficient metamaterial-based terahertz polarization converters that can rotate a linear polarization state into an orthogonal one. The metamaterial structure was created using flexible sheets capable of realizing near-perfect anomalous refraction. The design could be exploited to make flat lenses, prisms, and other optical elements such as high-performance spatial light modulators. The device could be scaled to work in the microwave to IR range, although fabrication challenges and metal losses can become issues when approaching visible frequencies that significantly degrade the device performance. The work was reported in Science.
That's it for this edition of Light Matters, the industry's only weekly newscast.
As always, you can write to us with your comments or questions at lightmatters@photonics.com.
Thanks for watching, and we'll see you next week.